So good day, our respective panel members and fellow professors, as well as students. Our study entitled Experimental Evaluation of the Flexural Strength and Crack Behavior of Foam Concrete Beams with Varying Density Levels aim to evaluate how sodium lauryl sulfate, or SLS, as a foaming agent affects the flexural strength, crack behavior, workability, and durability of foam concrete. So the study compared conventional concrete with foam concrete at the target densities of 1,200 kilogram per cubic meter and 1,600 kilogram per cubic meter using a constant 3% SLS concentration. So now let us proceed to the defense questions.
Okay, so for the first defense question, how does the addition of the selected additive affect the flexural strength of the material compared to the control foam? So the addition of sodium lauryl sulfate or SLS reduced the overall flexural strength compared to the conventional concrete because the generated foam introduced more air voids, lowering density and weakening the cement matrix. However, the goal of the study was not to exceed the strength of conventional concrete, but to evaluate whether foam concrete could still provide acceptable flexural performance while reducing self-weight. So among the foam concrete specimens, the 1,600 kilograms per cubic meter mixture performed better than the 1,200 kilograms per cubic meter mixture because its lower foam volume resulted in fewer pores and a denser internal structure. Therefore, the study concludes that although SLS reduces flexural strength, proper density control can still produce practical lightweight concrete with acceptable performance. Now let's proceed to the second defense question.
Okay, for our second question, what percentage or amount of the additive provides the best improvement in strength relative to the control mix? The study used a constant 3% SLS concentration for all foam concrete mixtures, so the variation in strength was mainly influenced by the amount of foam introduced into the mix rather than the SLS concentration itself. The objective of the study was not to produce higher strength than conventional concrete, since adding foam naturally increases air voids and reduce overall strength. Instead, the research aimed to evaluate how foamed concrete can achieve a balance between lightweight properties and acceptable structural performance. The result showed that all specimen groups gained flexural strength as curing age increased from 7 to 29 days. The 1,200 kilogram per cubic meter mixture increased from 6.167 MPa to 7.841 MPa, while the 1,600 kilogram per cubic mixture increased from 7.4 MPa to 8.104 MPa. The controlled mixture showed the highest strength, increasing from 8.409 MPa to 9.799 MPa. These results confirm that proper curing improves the flexural performance of SLS-based foam concrete. Using the absolute volume method, the 1,200 density mixture contained approximately 46.1% foam volume, while the 1,600 density mixture contained approximately 28.13% foam volume. Among the foamed concrete specimens, the 1,600 density mixture consistently showed better flexural strength because its lower foam content produced a denser structure with fewer air voids. Overall, the 1,600 kilogram per cubic meter mixture provided the best balance between reduced weight and flexural strength, making it the most practical mixture evaluated in the study.
Okay, so thank you for that, Mr. Dalag. So moving on to the third question, how does the additive influence the workability or consistency of the material compared to the control sample? So the addition of SLS improved the workability and flowability of the concrete mixture because of the surfactant action of the SLS. So it reduced the surface tension of water and generated stable foam bubbles throughout the mixture. As a result, the foam concrete became lighter, more fluid, and easier to spread compared to the control concrete. However, excessive foam volume also created some challenges. So in the 1,200 density mixture, the higher foam content produced a highly workable mixture that became difficult to control during the casting. So the researchers observed some leakages, some small leakages issues in the wooden molds. So this so the mixture behaves similarly to high slump concrete. So compared to the control mix, the control concrete was denser and more cohesive, while the foam concrete mixture exhibited the greater flowability but lower stability at higher foam contents. Therefore, SLS positively influences the workability, but proper foam control and mixing procedures are important to avoid segregation, instability, and excessive fluidity.
Okay, so for the fourth difference question, what effect does the additive have on the setting time and early age strength of the material versus the control mix? So SLS indirectly reduced early age strength by increasing air voids, which lowered the density and compactness of the cement matrix. As a result, lower density mixtures gain strength more slowly due to the higher porosity and weaker particle bonding. So however, all specimens still showed increasing flexural strength with curing age, indicating continuous hydration. The 1,600 kilograms per cubic meter mixture performed better than the 1,200 density mixture because of its lower foam content and denser structure. So SLS mainly influenced the concrete physically by altering pore structure rather than affecting cement hydration chemically.
So for our final defense question, how does the additive affect the durability-related properties compared to the controlled sample? The addition of SLS affected durability by increasing air voids, which reduced density and increased permeability compared to the conventional concrete. However, SLS also produced a more uniform pore structure that influenced crack behavior. The controlled the control specimens showed branching cracks indicating better stress redistribution and ductility. The 1,600 density foamed concrete developed limited branching with better crack resistance, while the 1,200 density specimens showed mostly straight and localized cracks, indicating more brittle behavior due to higher porosity. These results support Rasmussen et al. 2017, which states that higher density mixes develop more distributed crack systems, while lower density foamed concrete tends to produce localized crack propagation. Although conventional concrete remained superior in durability, the 1,600 kg per cubic meter mix achieved acceptable performance for lightweight applications.
Right? So thank you for that. So in conclusion, the study demonstrated that sodium lauryl sulfate can successfully produce stable foam concrete with reduced density, as well as acceptable flexural performance. While conventional concrete is still achieved superior strength and durability, the 1,600 kilogram per cubic meter foam concrete mixture showed that a balance between lightweight characteristics and structural performance is achievable. So the findings highlight that density control is the key factor in optimizing foam concrete behavior. With proper mixture, proportioning, and foam regulation, SLS-based foam concrete has strong potential for lightweight structural and non-structural construction applications. So that's it for our defense video, and thank you everyone for watching this video.